Hi everyone. So in the last class, we all learned how to apply binary search on an unsorted array, right? And we are going to extend our vision of applying binary search on unsorted array to this class as well with a very interesting question. So let's take a look at it. So the problem says that you will be given an integer array of size n. Okay, now this integer array of size n, it can be unsorted. By unsorted, I mean it can be any random array. Okay, cool. So now that we know that this is the kind of input that we have, what we have to do is we have to find a peak element in array. Just get me a peak element in this array. Now, we should all first understand what do I mean by peak element. So for that, let's take an example. So if let's say I have an array that contains 10, 20, 15, 2, 23, 90 and 67. This is 23, yeah. So what is a peak element? So if you take any random element from this array, then that element will be a peak if and only if both the two conditions are true. First condition, that this element must be greater than or equal to the element in its right. Okay, and second condition is that this element must also be greater than equal to the element in its left. Okay, so basically if there is any array and let's say you consider ith element, then it has got two adjacents. So there is an adjacent in left which is at index I minus 1 and there is an adjacent in right which is at index I plus 1. So basically if you pick array of I and consider that to check whether that can be peak or not, then that element array I has to be greater than equal to the array I plus 1 also, and it has to be greater than equal to array I minus 1 as well. Okay, so that is the criteria for an element to be called as a peak element, right? So now if this is your array, how many elements do you see over here which can be regarded as peak elements? So just pause and think about it. Okay guys, so if we take a look, I can say that hey, this 20 is greater than equals to 10 and greater than equals to 15, so 20 is a peak. And how about this 90? This 90 is also greater than equals to 23 and greater than equals to 67. So 20 and 90 are the two peak elements in this array. So one thing that we should all notice that given a random array, there can be multiple peaks in it. But what is the question saying? Question is not asking you to print all the peak elements or to return all the peak elements. It is simply telling you find any one peak element. Okay, so let's call it find any peak element in array. So you can return 20 from your function, then also it passes. You can return 90, then also it passes. Okay, cool. So now that we have understood this thing, all of us can solve it using a linear search, because the rule simply says that your a of I should be greater than equals to a of I minus 1 and a of I should be greater than equals to a of I plus 1. That is all which I want. See, there is an equality. Okay, so basically I can say in literal terms that an element is peak if it is not smaller than its adjacent elements. Okay, so if it is not smaller than its adjacent elements, then it is peak. Okay, so you can have a linear search in which you are kind of just checking for every a of I, you're checking for this condition, and then based on that you're marking it as peak. You're calling this is a peak. Okay, now when we are clear with this thing, there is one important thing that we all should keep in our mind. Here you are playing with the indices, right? So it might so happen that for some elements there might not be a left element, and for some elements there might not be a right element. Can you guess which kind of special elements they would be? So just pause and think about that. So guys, I believe it is easy to think. So if you consider array of 0, then there is nothing in the left. Okay, similarly if you consider array of n minus 1, then there is nothing in the right. So how to decide whether they can be peak or not? So for that I would modify it a bit by saying that element must be greater than equals to right element if the right element exists. Similarly, element must be greater than equals to left element if the left element exists. Now what does it mean? So let's say you had something like 20 over here, then this 20 was also to be regarded as a peak because it does not have a left element, so I do not care about that, but it has a right and it is greater than equals to its right. Okay. Similarly, let's say if instead of 67 it was 97 or 90 or anything which would be greater than equals to this thing, then this would also have been a peak because there is nothing in the right, so I do not care about that. But whatsoever is there in the left, that happens to be smaller than or equals to it. Cool. So this should give you a thought that even the first and the last elements of the array can also qualify to be your peak elements. Okay, now come back to the original question which asks you to find any one peak and simply return that. So just pause the video and think about that for a while. Okay guys, so let's take an example. By example, I am trying to show you how to think a bit graphically over here because that will help us a lot. Let us make it 10. Then this goes, right? So let's say I'm going to create a graph containing x and y axis. So let's say x axis will contain index and y axis will contain a of index. So the indices, as you know, are going to be 0, 1, 2, 3, 4, 5, 6. So 0, 1, 2, 3, 4, 5 and 6. And on the y-axis you will have whatever the value is present at that index. So at index 0 you've got a 10, so here you have a 10. Here you have a 20, at index 1 you have 20, okay. At index 3 you have a 15, okay, and then here you have 2, and then here you have 23, so at index 4 you have got, let's say, 23. Here you have got a big one, 90, and here you have got 67, let's say this. Now if you connect these points, then you will get some kind of graph, right? So let us just draw that. This is the kind of graph that you are getting, right? Now you can say that, hey, this 20 is right here, this one, okay? And it is a peak, right? It is a peak. Similarly, this is also a peak and this corresponds to 90, right? Now why I have drawn this graph is because it gives you an idea that, hey, an element is being called as peak if that in literal terms is also a peak and that happens to be not smaller than its adjacents, which are left and right. Now think of it in this way. Let's say you are trying to somehow use binary search over here, okay? What do you actually do in binary search? See, there are two components. First component is how do you detect whether you are at answer or not, okay? So here, if you have to detect if your array of mid corresponds to answer or not, what is it that you have to check? You just have to check that array of mid should be greater than left as well as right. If that is the case, you'll be happy enough to return that array of mid as the answer. So if let's say you had an array where your array of mid was 23 and left side had 11, right side had 22, and this was your mid, and here you would have happily said that, hey, this happens to be neither smaller than left nor smaller than right, so this is your answer. But what if that was not the case? What if you had something called as 19 over here, okay? Now you have a 19 over here. If you take a look at this 19 is greater than equals to 11, but it is not greater than equals to 22, okay? So in this case, which side of the array would you have chosen? Would you have chosen to move in the left part or would you have chosen to move in the right part? That is an important question which you must ask yourself. So just pause and think about that. Okay guys, so let us think a lot of things over here. So it might so happen that in this part you had an 18 over here and then you had a 10 over here, something. So there could be a peak in this part also, right? And let's talk about this part. So in this part also, let's say you immediately had something called as 20 over here, then you could have had a peak in this part also, because 22 happens to be greater than equals to this and greater than equals to this, and same is the case of 18 when compared against 10 and 11, right? Now, I'm not really sure whether my answer can lie in this part or it can lie in this part, right? Because you know that there can be multiple peaks, and this is giving you a glimpse of that. What would you want? As a programmer, you would want to move in that part which is guaranteed to have an answer, which is guaranteed to have a peak. So you want to move to part which is guaranteed to contain at least one peak. At least one peak. Okay, because you know that there can be multiple peaks in this part, there can be multiple peaks in this part. When you think of the worst case is that you move to a part which does not have a peak. Now moving to a part which does not have a peak is going to be, very, very bad for you, right? So you would want to move to that part which definitely has at least one peak in it. Now how to determine that? How to figure out that which part is the part which will have at least one peak for sure? Okay, so maybe again pause and think a bit about it. Okay guys, so see, whenever such situation happens that array of mid is not a peak element, then what will be the scenarios over there? The scenarios over there will be that there is at least one adjacent element which happens to be greater. There is at least one adjacent element which happens to be greater. In the worst case, it can happen that you had over here 110. So in the worst case, it can happen that, hey, this right side element was also greater and left side element was also greater. But let's for now talk about this case where the right side element is greater and left side element is smaller. So think of the case if you would have moved to this part. Let's say you would have moved to left part. Then in the worst case, what would have happened? Just think about that. Okay, so just pause and think about that. So guys, see, the worst case could have been something like this, that the contents of this side would be something like 11, 10, 9, 8. Would you end up getting any peak in this part? Is 11 a peak? No, because 19 is greater. Is 10 a peak? No. Is 9 a peak? No. Is 8 a peak? No, because right side element is again greater. So here, what you did, you considered the part where the adjacent element was smaller. Okay, so in that part, the worst case could be that this is a part which was kind of in ascending order, and if there is a part which is in ascending order, in that part you end up seeing that, hey, there is no peak at all in that part, right? So that is a problem which can happen. Now tell me one thing, what can be a similar worst case in this part? See, here you started hunting for peak from here and you could not find any peak till here, right? Till the first point. In this part, the worst case could have been something like this, that after 19 you have got something like 22, 23, 24, 25. So see, this 22 is not your peak because 23 is greater. 23 is also not a peak. 24 is also not a peak. But how about 25? The answer is 25 is a peak over here because it does not have a right element, and whatever is the left, that happens to be smaller than or equals to that 25. So I can say that moving to that side, moving to the part where adjacent element is greater makes more sense, because even in the worst case, what would happen is that the last element would happen to be the peak. But moving to the part where the adjacent element was smaller does not make sense, because in the worst case you would not have a peak at all. Okay, so that is an important thing to understand over here. Now let us understand why is that happening. So for example, if I give you an array A1, let's say array A1 contains 10, 20, 30, 40. Can you tell me what will be the peak of array 1? So just pause and think about that. So guys, as you all can see, this is an increasing array and the peak over here will be 40, because 40 is the only element which is greater than the left and there is no right to it. Okay, had there been a right to it, then this 40 would not have been peak, the rightmost element would have been. Okay, now let's consider a reverse sorted array which contains 40, 30, 20, 10. So when you consider this array, what will be your peak? So here your peak will be first element because that is the only element which is greater than right and there is no left to it. Okay, for all the other elements, if you consider, they are greater than right, but there is a left which is greater than equal to them, right? You know, this kind of behavior got seen over here, and that is the reason why it makes sense to move in that part which is kind of increasing, okay, and not to move in that part which is kind of decreasing from here. Because if you take a look at this decreasing part, so see this 11, see if you are considering this thing which is kind of increasing, then only the last element of that part can be your answer, okay. But here this 11 cannot be the last element of the array because you had a 19, okay. Now if this 11 cannot be your answer, anything that comes before 11 can also definitely not be your answer, okay. But here that is not the issue because here if you consider this part, there will be a last item and that last item will be greater than its left and there will be no right to it, so that will be your answer. Guys, we can understand this thing graphically as well, and now let's try to understand that. So let's say there is an array and you picked any random mid. So at mid there was some value, let's say that value was equals to this much, right? And this is your m plus 1. At m plus 1 you had some value, and this is your m minus 1 where you had some value like this, okay. Now see, from here the graph is growing if you consider this part, and if you consider this part, the graph is kind of, you know, decreasing. So talk to me about one thing. If a graph grows, what are the different things that can happen to that growing graph? So just pause the video and think about that. So see, growing graph can be thought of like growing numbers. So a graph that grows, either it will keep growing and then at some point it will come down. The moment you say that it will keep growing and at a point when it will come down, there will be a point where it will come down, it is guaranteed that it will have a peak, right? And in the worst case, what can happen is that this graph just keeps on growing. Even if that is the case, then the last element would naturally become the peak, right? And which is what had happened over here. But if you move in this part, if you move in this left part, then you might be in trouble, because if this part is continuously decreasing, then there will be no peak at all in that part, as you can see over here. Even the first element is not the peak, okay. So what is the rule of thumb that we'll stick to? Very simple. You attack the middle element, and if the middle element happens to be your peak, you are happy, you got your answer. And if your middle element is not the peak, then you choose to move in that side where the adjacent element was greater, okay. Now in certain cases it might so happen that right element and left element both are greater. So in that case the situation could have been something like this, that this was your mid and you had a value over here like this, and at m plus 1 as well as m minus 1 you had greater values. So you can choose to move in this part also, and you can choose to move in this part also, because a graph which kind of grows from here will either come down or will keep on growing. In that case the last element will be answer, and the same thing applies in this part as well. So in such a situation where let's say you had 110 over here and 22 over here, you could have chosen to move randomly either in right or left. Both of them would have made the same sense, okay. So that's the entire idea over here. Cool. So just pause the video for a while and now just think about the time complexity, and also think about the implementation details and the corner cases associated with it. Okay guys, so first thing was time complexity. So we are seeing here that, hey, we attack mid, and then either our mid is answer, or what we do is we consider either the right half or the left half. So similar to binary search, right, that you are reducing your search space by half every time, okay. So in log of n base 2 time you will be able to get at least one peak, okay. Cool. Now implementation detail. When you implement it, then what are the things that you have to be cautious of? So see, whenever you attack m, what is the first thing that you do? You first check if a of m is greater than a of m plus 1 and a of m is greater than a of m minus 1 as well, then you return m. Now you have to be a bit cautious while doing this thing. So you should not make this check for this element and this element. So they have to be handled in a separate manner. So if your m is equals to 0, then you will just compare it against the right element. And if your m is equals to last index, then you will just compare it against the second last index element. Okay, and based on that you will decide whether they can be peak or not. Otherwise you will move. So if you were here and let's say if this cannot be peak, then you will move to the right side because there is no left side. And similarly, if this cannot be the peak and you were here, you can move to the left side. In the other cases, if your index is anywhere in this sandwiched area, then you are free to make this check. And depending on the result of this check, you will either say that m is the index where your peak is located, or you know where you have to move to, right? You have to move to the part in which the adjacent element was kind of increasing. Okay, cool. So that's about the implementation detail. And guys, by now we have seen a variety of arrays. We started binary search on a simple array, then we kind of rotated that array, and then we took a random array. But we saw that still the very essence of binary search continued to make its sense. Okay, cool.